The Superman lie. Do you remember that scene in Superman? He takes a lump of coal, squeezes it in his fist with immense pressure, and opens his hand to reveal a sparkling, perfect diamond. But is that really how diamonds are formed? Actually, no. That scene is a complete lie. If you squeeze coal, you don't get a diamond. You get, well, compressed coal. Maybe some graphite if you heat it up enough, but you will never, ever get a diamond. Why? Because almost all diamonds dug up today are older than the first land plants. Coal is fossilized wood and plant matter. Diamonds were forged deep inside the earth, usually between 1 and 3 billion years ago, long before life had even crawled out of the oceans, let alone formed forests to turn into coal. So if they aren't made of crushed coal, what are they? And why does the universe seem to go through so much trouble to make them? To understand a diamond, we have to stop thinking of it as a gem. We have to think of it as a survivor of a journey so violent and improbable that, statistically speaking, it shouldn't exist at all. And yet, what is truly amazing is that this invincible crystal isn't made of some rare, exotic element. It is built entirely from the fundamental building block of life itself. The carbon paradox. At its heart, a diamond is chemically simple. It is made of carbon. Just carbon. The same element found in the graphite of your pencil, the soot in your fireplace, and the molecules making up your own DNA. Diamond is the hardest natural material on Earth. But what actually makes it so tough? Deep underground, the physics is governed by density. High pressure thermodynamically favors the form of carbon that takes up the least volume. To achieve this higher density, carbon atoms must pack together much more closely than they do in graphite. Carbon generally has 4 valence electrons, giving it 4 potential connection points. Under normal conditions, like in graphite, it prefers to bond with only 3 neighbors. This creates strong, flat sheets. But these sheets are barely holding on to each other, connected only by weak electrical attractions called van der Waals forces. This structural weakness is why graphite flakes apart so easily. But deep underground, to survive the compaction, carbon is forced into the only configuration that minimizes volume. It must use all 4 electrons to form single bonds with 4 distinct neighbors. This forms a dense, 3-dimensional tetrahedral lattice. This structure is hard for 2 precise reasons. First, the geometry is rigid. Unlike the loose sheets of graphite, a triangle-based pyramid cannot shift or slide. Second, the bond density is enormous. Because carbon is a tiny atom, these bonds are incredibly short and therefore incredibly strong. While diamonds are stable deep underground, they are unstable at the surface. As the pressure drops, the carbon atoms naturally want to rearrange themselves back into graphite. If a diamond travels up slowly, the heat gives the atoms enough time to shift, and the diamond turns into a black lump of carbon. To survive, the diamond has to outrun this reaction. This happens through a rare event called a kimberlite eruption. These are deep volcanic pipes powered by huge amounts of gas, like carbon dioxide and water vapor. As this gas expands, it drives the magma upward at incredible speeds. The diamonds are shot from the hot mantle to the cool surface so fast that the atoms don't have time to rearrange. They get frozen in their high-pressure form. We haven't seen one of these eruptions in human history, but without this high-speed elevator, every diamond would have turned back into graphite long before we found it. So if these supersonic volcanoes erupted millions of years ago, where do we find the diamonds today? For over 2,000 years, India was the only source of diamonds on Earth. They weren't digging deep mines. They were sifting through riverbeds. You see, while the soft volcanic rock of a kimberlite pipe erodes over time, the diamonds inside are indestructible. They wash out of the rock, travel downstream, and settle in the sediment. These are called alluvial deposits. The famous Hope diamond wasn't mined from a pit. It was likely plucked from the mud of a river in Golconda. By the 1700s, India's supply ran low, and the focus shifted to Brazil. Gold miners in the Amazon started finding heavy, strange pebbles clogging their pans. They were raw diamonds, again, alluvial stones washed miles away from their source. The game changed in 1867 in South Africa. After finding a stray diamond on a farm, prospectors didn't just stay in the river. They tracked the stones upstream until they found something new, the actual mouth of the ancient volcano. This was the discovery of the kimberlite pipe itself. For the first time, humans stopped waiting for nature to wash the diamonds to us. We started digging straight down into the crust to get them. Today, we use massive industrial technology to recover these stones. But the true value of a diamond isn't the mining. It is the miracle of its survival. Every natural diamond is a time capsule, forged deep in the earth between 1 and 3 billion years ago. To put that in perspective, they didn't just exist before the dinosaurs. They are billions of years older than the very first dinosaur to walk the earth. They survived the crushing pressure of the mantle and the violent supersonic explosion that brought them to the light. When you hold a diamond, you are touching the most invincible material our planet can create. It is a piece of the deep earth, frozen in time, that simply refused to break. That is why, regardless of marketing, it remains the ultimate symbol of forever.